Welcome to Math 31. This is a continuation of the lesson on applications of the derivative. And I'm just going to go through a couple examples, sort of different looks of some fairly elementary applications. Now by the elementary I mean these are ones where we're given an equation to work with. The next batch, or soon, we get ones where we have to develop our own equations, and then that introduces a new sort of level, takes us to a new level. But anyways, here we have an object moving in a straight line from a fixed point, and its displacement in s in meters is given by that formula. T greater than or equal to 0 with t in seconds. So it is just typical for this type of application. The clock starts at t equals 0. And these are the four questions we want to ask. Not a lot different than the one we were looking at before, but the difference with these questions, they're all simple because the math is simple, but it's reading the question carefully and making sure you know exactly what's being asked for. It can be a bit of a problem. Oops. So, well, let's do A, I guess, first off. So when does the object reach its maximum displacement? First question. Well, for a problem like this, we need to be thinking, when it reaches its maximum displacement, what really is being asked for is when is v at t equal to 0. So it would make sense for us, given that we're provided with the position function, it would make sense for us to recognize that the velocity function is equal to the derivative of the position function, so s prime at t, which is equal to negative 4t plus 28. And we set this to 0, get a very simple equation to solve. So 28, excuse me. So t is equal to 7 seconds. So if you were to graph the original function, you would note that this is where it is reaching the top of the curve. And then for B, the question is when, or find the maximum displacement. So what then we want is, seeing as we know that it's reaching that point at t is equal to 7, we want to find s at 7, its position at that time. And by the way, as I mention all the time, frequently, pause me and go through the question if you want, and then check your answer. So s at 7 will give us negative 2 times 7 squared plus 28 times 7 plus 45. And then we just drive it through. So negative 2 times 7 squared plus 28 times 7 plus 45, and should get s at 7 is equal to 143 meters. So I'll write that out. Its maximum height is 143 meters. Then for C, it asks us what is the object's average velocity from t equals 0 to t equals 8. Now this can be a problem because we have a function for velocity, but if we plugged in v at 8, this gives us its instantaneous velocity at t is equal to 8. And even if we use that in conjunction with its instantaneous velocity at t is equal to 0, it's still not going to be good enough. So what we have to remind ourselves, fairly elementary physics, is that the average velocity is equal to the total distance that you've covered divided by the time. Now we know delta t is equal to 8, but what we can do to get its compare its difference in position, s at 0, if we find out where we're starting from, we would get negative 2 times 0 squared plus 28 times 0 plus 45. So s at 0 is equal to 45 meters. It's starting position, if you like. And then when you take s at 8, that's equal to negative 2 times 8 squared plus 28 times 8 plus 45. Should get 141 meters. So to get the average velocity, we take the delta t, which is the distance in position, or the difference in position, so 141 minus 45, divided by the time that's elapsed. And that should give you 96 over 8, which is equal to 12 meters per second is the average velocity. So that's how these ones work. And then finally for D, this is the easiest question. I don't know why I put this at the end, though we didn't really use it for solving other ones. But we want to find the rate of change of the object's velocity. Now, rate of change of its velocity, be careful. We're not looking for the velocity function. We want to get the derivative of the velocity function. The derivative of the velocity function is measuring the rate at which the velocity is changing. So when we take the derivative of this, it's just a matter, we've got our v function up at the top, so that would just be negative 4. And it would be meters per second squared. So this is actually equal to the acceleration. So you're losing 4 meters per second every second. Now the next example, I don't think I'll bother going through just because it's not that complicated. It's very similar. I'm not sure why I put this one up here. But I will give the answers for it so we can at least refer to that. If you want to do this on your own to check it out, there's actually quite a few examples or quite a few questions available in the textbooks, but 21,127 meters. And then how long will it take it to reduce its velocity to 100 meters per second? Answer is 55 seconds. So please try that out and then see if you get those answers. If you don't, you'll have to contact me and let me know if I made a mistake or whether you made a mistake. Next question is interesting. A very unusual type of application, or uncommon, I guess. The relationship between displacement and velocity is given by this particular formula. Now this is an odd one, partly because normally displacement and velocity wouldn't be organized in an equation this way. Usually you think of velocity as being the derivative of the position function or displacement function, which is correct. So this is a little bit different, and it's more of a question of dealing with the math rather than thinking of it as being a regular, normal application. But we do want acceleration. So we want to be aware that acceleration is equal to the derivative of the velocity function, so dv dt. Ultimately, that's what we want. And you could write it as v prime if you wanted, same deal. So what I'm going to do with this equation is I'm going to differentiate with respect to time. This makes sense to me because acceleration is the derivative of v with respect to t, and we're going to get that in that equation. And this is an example where we're dealing with implicit differentiation, even if you don't think of it in those terms. That's what you're dealing with, because we're taking the derivative, we're differentiating with respect to a variable that actually isn't even in the equation, and you can do that. So it's not like these regular questions we used to get, well, differentiate this, differentiate that, and always with respect to x. Here, we're taking it with a variable that is outside, that is not given to us. So we want to be careful. So d dt of the 1/3 s squared minus d dt of 4v squared is equal to d dt 12. So when we take the derivative of 1/3 s squared, we'll get 2/3, that's 2 times 1/3, 2/3 s, and then we have to be aware that we're going ds dt. Now you could write that if you wanted as s prime, which is what I usually do with implicit differentiation. I'm not going to in this case, and the reason for it is that I want, here it matters a lot. I want to always be aware of what variable I'm dealing with, and ds dt gives me more information than s prime, because it's telling me what variable I'm taking it with respect to, and I'm not comfortable taking chances on this one. So 4v squared is 8v, but then we get dv dt. Now pay close attention to that variable, because dv dt is what we ultimately want. And then the derivative of 12 is just equal to 0. Now when we do the manipulation on this, I'm going to bring this to the other side just to make it positive, and that seems reasonable. But I'm going to do one other thing here. S is, well, S is represents position. There's not much we can do with it. ds dt, however, we can change that. ds dt is equal to velocity. So this function can then be written as 2/3 sv. And then we take this to the other side, and we get 8v. And then dv dt, as was indicated at the top, is really acceleration. And so we just go after that variable. So I'm going to divide by 8v. So I get 2/3 sv times 1 over 8v. This is equal to a. And then the v's divide out, and the 2 and the 8 will divide. So we end up with 1 over 12 s, because the v's are gone, is equal to the acceleration. Kind of an unusual one, but it would mean that if this equation was actually correct, which we could assume that it is, I guess, that if you wanted to find the acceleration at any point, you would just go 1 over 12 times whatever the position was. So it's not an easy relationship to imagine, but that's the numbers work that way. So that will be it for this lesson, and the next lesson we'll just go on to some other variations of these things, leading us to related rates ultimately. So thank you for your time.